Hello, everything you need to know about limits and as quickly as possible. All right, let's do this. So, what is a limit? A limit. What does it mean? The limit as x approaches c of f of x equals r. What does it mean? As we get sufficiently close to c, but not equal to c, the value of f of x is arbitrarily close to r. So what we are saying is as you get really close to this x value, your function is getting really close to this y value, essentially, x and y. As you get really close to this x value, you're approaching this specific value on the function. Okay? So let's look at that in action. Look at the graph of h of x. What is the limit as x approaches 3 of h of x? Well, as you get really close to 3, where is your function headed? It's headed to a y value of 3. So as you get really close to 3 on the x-axis, the y value that you're approaching is 3. So the answer to this is 3. Okay, let's think analytically. What is happening as x approaches 1 of natural log of x? Well, just plug 1 in and you get 0. A lot of times that works. Direct substitution works. What about as a table? Well, look at the table of values. As x approaches 2, what is g of x equaling? Well, as you get closer and closer to 2, 1.9, 1.99, 1.99, look at the numbers. They're getting closer and closer to 4. Well, as you get really close to 2 from the other direction, 2.1, 2.01, 2.001, you can see those values are getting closer and closer to 4. So, voila, we know that the limit as x approaches 2 of g of x is equal to 4. So, you can think of this sentence, whether it's a graph, whether it's just a function handed to you, or whether it's a table. But the point is as you get really close to a specific x value, what is the y value? As you get really close to a specific x value, what is the y value that you're approaching? That's a limit in a nutshell. Let's continue on. So we can also have one-sided limits. So what does that look like in a graph sense? Look at this h of x graph. We could approach 4 from the left. So here's 1, 2, 3, 4. As you're approaching 4 from the left, what y value are we approaching? It looks like, if my drawing was perfect, it looks like 1. But as you're approaching 4 from the right, what y value are we approaching? It looks like we're approaching 2, sorry, not 1. 1, 2. And the other one, 3, 4, 5. Looks like 5. So you can see that the graph is behaving differently on the left than it is on the right. What about if you're just given a function? Okay, well, look at what happens when you plug in 1. You're going to get 0. So we can't divide by 0. So as we get really close to 1, what is happening? Okay, well, as we get really close to 1 from the left, say 0.999 minus 1, well, 0.999 minus 1 is equal to negative 0.001, and the numerator remains 1. And the closer we get this to 1, as it approaches 1, that means this solution is just getting smaller and smaller and smaller, but most importantly, it is negative. So 1 divided by this very small negative number is resulting in negative infinity. And think about what happens as you approach 1 from the right. 1 divided by 1.000001 minus 1. Let's just get really small really quickly. So as we get really close to 1 from the right, 1.00001 is equal to 0.00000, however many zeros I need, 1, a very small but yet still positive number. So 1 divided by that very small but still positive number is going to equal infinity. So it's really obvious on a graph what's happening from the left and from the right. But you have to analyze and think critically when you're given just the function. If every question was a graphing question, by all means graph it, and I bet the answer will be pretty obvious. But if it's not a graphing question, it might take some of this cheeky little 1.001 action. All right, what about this table? What have I demonstrated here? We're trying to ask what's the limit of g of x as we approach 0 from the left, and what's the limit as we approach 0 from the right. So here's a table. Which values are to the left of 0? The negative ones. So as you're approaching 0 from the left, what y value are we headed to? Looks like 4. But as you approach 0 from the right, the positive values, 0.1, 0.01, 0.001, it looks like we're headed towards 7. So we're answering the same question 3 different ways, and I think that's really good, right? That really is hopefully making you think, like, okay, here's how it looks on a graph. Here's how it looks on a table. Here's how it looks if I don't have either of those things. The idea is the same, but how you approach the table versus the graph versus the function might be a little bit different, but hopefully you've got the big picture. So we got these limits, we got these limits. Let's continue. Using properties. So when you have functions that look a little different or weirder, what do? At the end of the day, just direct substitution is your best bet. Direct substitution is your best bet. But I also want you to realize that you can sort of break it up into individual pieces, right? You could think of this as this times this, right? You can think of it as 2 separate things. You don't have to look at it as one behemoth function and get scared or intimidated. You can split it into chunks, okay? Now, at the end of the day, just plugging in pi is really your best bet here, because when you plug in pi, you're going to get sine of pi is 0 and e to the negative pi is something, right? But inevitably, it's 0. If you think of this, it's 0 times 1 over e to the pi, right? So the sine part gave me 0, the exponential part gave me this, and then you end up with 0 times that. Well, 0 times anything is 0. Okay? So, but splitting it into chunks is kind of what I'm trying to get across here with using properties. You don't have to do it all at once. So again, as we're approaching 4, we're running into an issue because 4 minus 4 is 0. Taking the square root of 0 results in 0. That's fine, but dividing by 0 is bad. So think about them individually, right? Maybe don't think about it all at once. Just think about, okay, what's happening to my numerator? Okay, whoops. And what's happening to my denominator? Is there, think about that as a whole. So actually, I'm realizing that this, let's do this 4 from the right, okay? I'm going to edit this on the fly, okay? I realized I didn't think that all the way through. So 4 from the, because you can't take the square root of a negative. Okay, anyway. Well, 4 from the right would be bad. Sorry, 4 from the left, right? Anything bigger than, no, 4 from the right. Sorry. I should have been more prepared on this. 4 from the right. Yeah, 4 from the right. Anyway, as you're approaching 4 from the right, what happens? Well, with x squared plus 4, just plug it in, right? 4 squared is 16 plus 2 is 18. So we know that this is headed towards 18. And we know that this is headed towards 0. But what I really want you to think is, okay, yes, it's headed towards 0, but how is it getting there, right? Is it coming from the bottom, right? Like, is it negative numbers that are approaching 0, or is it positive numbers that are approaching 0? And the answer is it's positive numbers. As you're plugging in, 4.001, right? 4.001 0.00001, you're getting the square root of a very small number, which is also small. So yes, this limit equals 0, but realize that, okay, it's 18 divided by tiny number, right? It's 18 divided by tiny number, so your answer is infinity. Okay, so these maybe aren't the perfect examples as I've titled this use properties, but what I'm trying to get across is that you can break it up into two separate chunks. Think about what's happening in the numerator, ignore the denominator for a moment. What's happening to the denominator, ignore the numerator for the moment, and then combine those thoughts into one. I know I'm getting closer and closer to 18. I know I'm getting closer and closer to 0, but what does that mean in the context of this fraction? 18 divided by something really small as it gets closer to 0 is going to result in infinity. And this next question I really like. So heads up, this next question I really like. What is the limit of g of x times h of x? And g of x is the graph. H of x is the table. What is the limit as x approaches 2? Interesting. So what is the limit of g as x approaches 2? It appears to be 2. Does it equal 2? No, but the limit is 2. So think about breaking this up into chunks. We know the limit as x approaches 2 of g of x equals 2. What's the limit as x approaches 2 of h of x? Well, as h of x, as x approaches 2, it looks like it's headed towards, so we get closer and closer to 2, closer and closer to 2, it looks like it's headed towards 3. So what's the answer to this? 6. The limit of g is 2, the limit of h is 3, multiply the two together, and you end up with 6. Interesting problem, right? So what about the quotient? Well, it's still the same answers, right? And so what's this one going to be? 2/3. So whether we know the function or not, we can still think about this in chunks. I can see the g graph, I can see the h table, and I'm thinking, okay, I know where g's headed, I know where h is headed. What does that mean when I divide these two functions? This problem is truly no different than this. It's just that here we knew the function, and here we can only, quote, see the function, right? But the idea is the same. Chunking it and thinking about how they will affect one another as you multiply or as you divide. Okay, continuing on. Some algebraic manipulation, right? Sometimes you look at a limit and you're like, wait a minute, 4 minus 4 is 0. And the square root of 4 is 2, and 2 minus 2 is 0. Oh no, 0 over 0. Does that mean the limit does not exist? Because what does that even mean? No, that's not what that means. It means you're going to have to use some manipulation. And the second you see a square root and you're getting 0 over 0, hopefully with some training and some practice, you think, I need to multiply by the conjugate. It's that radical that's giving us troubles. It's the radical that's weird, right? The square root of 4 gives us 2, and 2. That's the troublemaker. So multiply by the conjugate, and you end up with the limit as x approaches 4 of x minus 4 root x plus 2. So when this multiplied with its conjugate, it produced x minus 4, because root x times root x is x, and 2 times 2 is 4, or negative 2 times 2 is negative 4. So wait a minute, now this matches this. Oh, we love to see it. Go ahead and cancel that out, and you've got the limit as x approaches 4 of root x plus 2, and the answer is 4. Because you plug in 4, square root of 2 is 2, or sorry, square root of 4 is 2, 2 plus 2 is 4. So sometimes you end up with that 0 over 0, and you gotta use some algebraic manipulation. You might be thinking, is that the only way? Could I sort of guess and think about oh, if I get really close to 4, what's gonna happen, right? Well, if you get really close to 4, what is gonna happen? 3.999 minus 4 over square root of 3.999 minus 2. So you end up with what? Negative tiny number over negative tiny number? What is the square root of 3 point? Well, it's not that tiny, right? It's you see what I'm saying? Is that just, I don't see how that's going to get me 4, right? I can't. It's just, it's not quite there. It's not quite obvious. I know that this is essentially 2, right? And 2 minus 2 is 0. So yeah, I guess that, you see it, but negative tiny divided by negative tiny doesn't magically equal 4, right? Hopefully I'm getting my point across. All right. Another algebraic manipulation is simply the need to factor. This factors into x minus 2, x minus 1 over x minus 1 times x plus 1. These cancel out, and you end up with x minus 2 over x plus 1. And I forgot to point out, I'm rushing a little bit, I forgot to point out that when you plug 1 in, 1 squared minus 3 is negative 2, and negative 2 plus 2 is 0. 1 squared, 1, minus 1 is 0. It's another situation where you have 0 over 0, and you can't just not do the problem. You need to think, how can I manipulate this to not give me 0 over 0? You can factor, reduce, and try plugging it in again. Try plugging it in again. 1 minus 2 is negative 1 over 1 plus 1, which is 2. Negative a half. Yay! So by factoring and reducing, you change that 0 over 0 limit into something, well, solvable. All right. I'm on a roll. I know I'm talking kind of fast, but I'm trying not to make this the longest video in the world. I'm just trying to hit all the key topics. I hope that you find this video enjoyable and sort of refreshing you and reminding you and inspiring you to ask a good question next class. But let's keep it going. I got 2 more topics, discontinuities and IVT and continuity. So discontinuities and asymptotes. What is the meaning of this? As we go to infinity, f of x equals c. That means there's a horizontal asymptote at y equals c. As we go to negative infinity, the limit is equal to d. What does that mean? There's a horizontal asymptote at y equals d. As we approach c from the left, we're going to infinity. What does this mean? There's a vertical asymptote at x equals c. As we approach c from the right, we're also going to infinity. What does this mean? There's a vertical asymptote at x equals c. Now, why? Well, horizontal asymptotes happen on the ends of the function. In your other classes, we often define it as end behavior. Where is the ends of the graph? The ends of the graph are on the extremities towards the x values, infinity and negative infinity, right? So when a limit is x approaches infinity, we are describing a horizontal asymptote. But as you approach a specific x value, which we're calling c, and the limit equals infinity, that is a vertical asymptote, because what we're saying for horizontals is that as you go to infinity and negative infinity, there might be all kinds of craziness happening in here, but by the time you get to infinity, you're leveling out at a specific y value. There might be all kinds of craziness in between, but by the time you get to negative infinity, you're leveling out to a specific y value, and thus the horizontal asymptote was born. But what we're saying with these next two is that as you get really close to a specific value, not infinity and negative infinity, but a specific number, your function is headed towards infinity. And that is what's creating a vertical asymptote. So they both talk about infinity. As x goes to infinity, horizontal asymptote. If your limit equals infinity, vertical asymptote. Couple more. What if the limit equals something, but your function doesn't equal that? What are we creating? A hole, right? We know the limit exists, but yet the function isn't defined there, and thus a hole was born. We know the left-hand limit equals this, and the right-hand limit equals something different. What does this mean? A jump. So, look at the graphs now. Let's write some limit statements based on the graphs. What have I drawn here? A horizontal asymptote. So that means the limit, and where is this asymptote happening? Over here to the left as we go to negative infinity. Let's call this thing f, I guess. So this asymptote can be described with this limit. As we're going to the left towards negative infinity, we're approaching whatever y value this is. And I'm using r as a generic thing, right? It could be 2, 3, 4, 5,000. It can be anything, right? It's just as we're going left to infinity, we're approaching a specific value. And similarly here, I'm doing all kinds of weirdness, right? I'm shooting up over here, wiggling in the middle, but by the time we get to positive infinity over here on the right, we're starting to bottom out at a specific y value. So as we go to infinity, we're approaching s. Okay? And here's some vertical asymptotes, right? What's happening here? So again, let's just call this thing f. As we approach it from the left, as we approach what from left? C. As we approach this c value from the left, what is our function doing? It's shooting up towards positive infinity. So as we're approaching c from the left, our limit is infinity. And similarly, as we're approaching it from the right, where is our function headed? Down to negative infinity, right? So as we're approaching c from the right, we get negative infinity. So again, here are statements, and we were saying, what does that mean on the graph? Here's graphs. Now, can you write a statement that's true, right? I'm just going both ways here. So I hope that's like enlightening and connecting some dots. So what is true here? Well, we know, and let's call this R, okay? And let's call this point S. We know the limit as x approaches c is equal to r, right? We see the left and the right hand limit approaching the same point. So we know the limit exists. But does the function exist there? No. F of c equals some other number s. And because r does not equal s, that's why there's a hole. The limit exists, but the point exists somewhere else, and thus a hole. So that's how we could summarize this graph. And here, we can see that the left and right hand limits are just completely different. As we approach c from the left, we're up here at r. And as we approach c from the right, getting sloppy, we're down here at, again, just randomly calling it S. Okay, I like this moment right here. I hope you stayed with me there. Again, you can slow me down or remind me or whatever, but I hope that's connecting dots, like the statements with the graphs and the graphs with the statements and how those are related. All right, let's take it one step further with continuity and IVT and call it a day. Miraculously, this video might be under 30 minutes. So, for what value of k is f of x continuous? I've asked an interesting question here. We didn't do this in class, but get over it, okay? For what value of k is f of x continuous? So, what does it mean to be continuous? Remind yourself. So, here's f. The limit as x approaches 1 from the left needs to equal the limit as x approaches 1 from the right, which also needs to equal f of 1, right? The summary of continuity was the limit needs to exist, the function needs to be defined, and both of those things need to be the same, equal. And that's what I'm writing here. The function is defined at 1, the left-hand limit and the right-hand limit exist, but even more so, all three are the same. We need to make that true. And why did I choose 1? Because, well, that's where the piecewise defined function is being split up. So here's this k value that's giving us trouble. But focus on the first function that we know everything, right? What is the limit? I'm sorry, I apologize. I kind of wrote these backwards, right? Usually this one comes first, the less than 1, and then the greater 1 comes second. That was brain fart of mine. But so x greater than or equal to 1 is the stuff on the right, right? The limit as we approach 1 from the right, okay? So what is the limit of f of x as we approach 1 from the right? It is, just plug in 1. 1 times a half is a half. A half minus 1 is 1.5, or 3/2. And I'll also ask, what is f of 1? Can we solve for f of 1? Well, it's also 3/2, right? The limit of this is 3/2. This line that's going up, right? But yeah, the line that's got a positive slope, up 1 over 2. But as you're approaching 1 from the right, you're approaching 3/2. But it's defined there, right? At x equals 1, it is the line, right? So these two things are the same. So what does that mean? We need to make this also 3/2, right? As we approach this, as we approach 1 from the left, we're talking about this piece of the piecewise function. So somehow we need to make this equal negative 3/2 when x is equal to 1. Do you follow that? We know the left-hand limit, we know the right-hand limit is 3/2. We know at x equals 1, the function is 3/2. The only final piece is that the left-hand limit matches this as well. So we need that other piece to be equal to 3/2. When? When x is equal to 1. So negative x plus k needs to equal 3/2 when x is equal to 1. So in other words, negative 1 plus k needs to equal 3/2. So k equals 3/2 plus 1. Get a common denominator, and k equals 5/2. So I made you use the definition of continuity, but also made you do a little bit of algebra in order to solve for that value. How's that make you feel? Maybe run it back if I lost you. The last one. Maybe I should have wrote this up here. The last one. I've got this g function. If g of x is continuous, how many zeros are there? Could g of x equal 3? Could g of x equal 5? Let's focus on the first question, and definitely a potential AP question. How many zeros are there? Well, if g of x is continuous, what we're saying is that if this point exists and this point exists, then between -1 and 0, we had to hit -4, -5, and -6, and everything else in between, right? We have to hit every value between -3 and -7. And then from here to here, we have to hit every value between -7 and 2. And is 0 between -7 and 2? Yes, it is. We just hit a 0. There is a 0 somewhere between 0 and 1. And if, again, g of x is continuous, and we know this point exists at 1, and we know this point exists at x equals 2, then we have to hit every value in between, which isn't a whole lot, but 2.1, 2.2, every number in between, including 3, up to 4, right? But is 0 between 2 and 4? No. So the only time you're guaranteed a 0 is here. 1, 0 between x equals 0 and x equals 1. We are guaranteed a 0. And if we put this on a graph, -1, -3, 0, 7, -7, 1, 2, and 2, 4. If we drew only straight lines, there to there, there to there, there to there, right? That's a continuous function. And as you can see, there is only the 1, 0. Could there be another 0? Sure. The graph could have looked like this, right? No one's stopping the graph from looking like that, right? Like it could be the squiggliest function ever, but we can guarantee only 1, 0 based on intermediate value theorem, okay? Intermediate value theorem says if your function is continuous and you know that these sets of points exist, then every point in between must exist. So could we be equal to 3? Or must we be equal to 3? Yes, we must be equal to 3 somewhere between 1 and 2. Because if the function equals 2 at some point, and then 4 at a later point, it had to hit 3 as it made its way up to 4. Could or must it equal 5? Could is definitely a different question than must. Is 5 between these two numbers? Is 5 between these two numbers? Is 5 between these two numbers? No, no, and no. So must 5 exist? No. Could 5 exist? Of course. It could, a function could be anything, right? Functions behave like craziness all the time, but there's only a certain amount that you can guarantee, especially by intermediate value theorem. All right. And with that, I covered a lot and did a lot. I hope you enjoyed it. I hope you learned something. I hope you reminded something. I hope you have a question when you come to class. That's all I got, folks. Appreciate your time. If you made it this far, leave a comment that says, I heart limits with a smiley face. Okay? All right, whatever. See ya.